Okay, so we're going to have a look at a concept called Pedersen Commitment, and this is a way that Bob can commit to a secret to Alice and then possibly reveal the secret at some time in the future. Alice cannot tell what the secret is that Bob holds, and Eve has no way of telling what the secret is if she can't see the secret that's passed between Bob and Alice. It's often defined as a perfect secrecy method, as what we can do is that Bob can create a secret and then send Alice a commitment. In this case, we'll define the commitment as a C value, a commitment, and an R, which is a random value. So Alice can keep those values, and then at some time in the future, Bob can then reveal the secret to Alice, and Alice checks the secret against the commitment. With the commitment, it's not possible for Alice to determine what the secret actually is. In this way, Alice can verify the secret tallies up with the commitment. So one way we can do this is with discrete logarithms. And with these discrete logarithms, what we do is we take two prime numbers, large prime numbers hopefully, P and Q. And then we create a generator value, and we make sure that the generator value will give us unique outputs for every value up to the value of Q. Then what we do is we create a secret value, S, a random secret between Z, 0 and Q. And then we calculate an H value, which is G to the power of S mod P. So the public values that we have are P, Q, G, and H. And Bob can go ahead and publish those. Whoever is the sender then takes a message and a random number and calculates G to the power of the message, multiplies that by H, which we've just calculated, to the power of R, our random value, and then takes a mod P. This becomes the commitment. So the value of C and R is the commitment that Bob will make to the secret that he knows. The secret in this case is the message M. The verifier then verifies the secret when Bob reveals the secret as G to the power of M times H to the power of R mod P. If the value matches with the C value that Bob sent, then Alice will be able to confirm that the secret tallies up with the commitment. So here is our setup. There's our P. We'll get a prime number here. And then we'll create a Q value, which is another prime number. We'll just multiply the prime number by 2 and add 1 onto it to make sure that we get a prime number. And then we'll calculate a G value in there between 1 and Q minus 1. And we'll create our little random value S between 1 and Q minus 1. Then we'll take G to the power of S mod Q to give us our H value. This gives us our H value here, which is G to the power of S mod Q. Those are the public values that we can publish related to the commitment. So here is the code that we're going to use. In this case, we've got two values. We create a verifier and a prover here, and we'll set up the parameters each time with our commitments. So we'll have two values, message 1 and message 2, and we'll create two commitments for it with two R values here. As we'll see, we can use homomorphic encryption to be able to add the two values together, which is multiplying the two commitment values. But here we can actually prove our commitments with this function here and here. And if the result tallies, we'll get a true result back. So let's see if we can view that. So here's an example run. There's our secret. We have a P and a Q value here, and then there's the G and the H value. In this case, we've got our messages here. It will then create two commitment values with the R values, and then when we verify it back, we get a true value for the commitment on message 1 and a true value on message 2. We can add the two messages together, which is multiplying our two commitments, and we'll end up be able to verify the addition. This is called homomorphic encryption, and we'll look at that in a little minute. Okay, so let's take an example here. So we have, say, 15 as a value that we want to commit to, and then reveal the result, the secret, and then 70. In this case, we'll prove both of them with a commitment, and then we'll verify them in the end. Then what we'll do is we'll add the two values together, and we'll have a commitment for that, and we'll see if that can be proven. So we'll go for 15 and 75. So we generate new values here, 15, 75. Our first commitment is this and this. Our second commitment is this and this. When we run the code, we get a true when we reveal the original value back and the commitments. And the same happens when we multiply the two commitments together. We get the equivalent of adding message 1 and message 2, which in this case will be 90. And then when we take the addition together, we see that we also get a true on that. That's defined as homomorphic encryption. So here's the code here that we saw. So this is the proving of that equation, g to the power of x mod q multiplied by h to the power of the sum. In this case, it can be just one value if we want, mod q, and we take mod q of the whole lot. So that was the little equation that we saw for our proving there before. Okay, so that shows us our code. So here is one example where we could use a blockchain-based voting commitment. So in this case, the election is held here. So Alice wants to know what Bob's vote was and for him to prove it at some time in the future. So Bob will make his commitment onto the blockchain, of which Alice can actually look to see that Bob has made the commitment before the election starts. So when the election is finished, then after he's done his voting, then Bob can share his secret. So it might be, I voted for the silly party in here. So she takes that message and then she looks at the commitment and then checks that I voted for the silly party here with the commitment, and she will make sure that actually he made the commitment before the end of the election, and this shows his answer, his secret. In our previous example, in this example here, no one can tell what the secret was. Only Alice will know, and Bob doesn't have to actually give away the secret. All that's contained here is the commitment, and no one can find out what the actual secret value was from here. So as long as Alice keeps that secret, then no one else will know what that is. Again, as I said, Bob could keep it secret forever and might be forced to reveal his answer there. But as we saw before, we could use a homomorphic encryption method to be able to add things together. And this is what we can do with the method that was shown with discrete logarithms. We can take the two commitments and we can multiply them together as values, and that's equivalent to adding the two votes together as a commitment. So we might be able to take all the votes together and then take all the commitments together and then we can get a tally for all the votes. In this case it's 30, and then we can have a final commitment to 30 for all the votes, and we'll be able to post that as a commitment here. So if we want to have a look at the code again, we can actually see how that actually works. Okay, so here is an add method in Python, and we can see that we take our values and we multiply them together. So we would take each of our commitments, C1 and C2, and we take one at a time, and then we will then multiply them together to give us our output. So this is the equivalent, this is the pointer to the values that we get. We can put lots of commitments in there, and then we will go round and round, multiplying each one together, taking the mod, of course, of our Q value in the end, and returning back the overall commitment. Okay, so in this way we can actually operate on our commitments without actually revealing the original values. This is an example of homomorphic encryption. Okay, so there's the code that we've got there. As I said, there's the add function, and in this case we're passing the values here, the two commitment values, into here, and we're multiplying them together, and that's equivalent to adding and then returning the value back. In this way we can get a commitment for all of the votes cast. Okay, so that's been an introduction into Pedersen's commitment, and you can see that the method itself has an excellent grounding in a way of keeping things secret, where Bob can actually commit to something, make that public so that everyone can see his commitment, but then can then reveal it to whoever he trusts. He might never want to reveal it. The other advantage we saw with this type of commitment with discrete logarithms is that we can use homomorphic encryption to be able to operate on values, but still in a completely private way. We can also use elliptic curve and Elgamal for this type of method, and these give us different types of properties. But the method I've explained here uses discrete logarithms to implement the commitment. Thank you.